Hi, welcome to my YouTube channel Human Learning. I am back with the part 4 of series of lectures that I will be conducting on machine learning, and today's video is about multiple linear regression. Okay, before going through this video, I would highly recommend you to go through my previous videos in this series so that you get familiar with the terms introduced in those videos and you will also get a better understanding of the concepts that will be introduced in this video. Having said that, let's get started. Till now, we have been dealing with only one input, that is one independent variable, and one output of the form y equals a capital X plus b. This was handled using single linear regression model. Now multiple linear regression model deals with problems where we have more than one input and a single output. This is just an extension of single linear regression model. Here the predicted output is represented as the weighted sum of the inputs. Let us consider a case where we have two inputs x1 and x2 and a single output capital Y. So our predicted output y will be represented as y equals w0 plus w1 x1 plus w2 x2, where w0, w1 and w2 are the weights attached to the inputs. The goal of the multiple linear regression model is to find the optimum values of the weights w0, w1 and w2 such that our prediction becomes a close approximation to the actual output capital Y. Now let us find the optimum values of the weights w0, w1 and w2 for the given dataset using multiple linear regression model. First, let us substitute the values of x1, x2 and capital Y in the given equation as 0, 1 and 9 to get w0 plus w1 times 0 plus w2 times 1 equals 9. Similarly, we'll get the following equations. From this, you can see that we have 5 equations and 3 unknowns w0, w1 and w2. We need to solve these equations to get the value of w0, w1 and w2. Let us first represent this equation in a matrix form. So if we are able to find exact values of w0, w1 and w2, then this will become an ideal case where there will be no error associated with this model and everything will be fine. You know, we live in a real world and so the errors are inevitable. Let us call this matrix as X, this matrix as W, and this matrix as Y. So in ideal situation, we would have XW equals capital Y. But what we find is that no exact solution exists for this equation. So what we will do is that we will find the optimum values of W such that our equation becomes xw equals small y, and we'll find this optimum value by minimizing the errors associated with xw equals y. Now what I will do is that I will just give you the formula first and find the value of w using that formula, and then in the later section of this video I will derive this formula. So the optimum value of weight W is given by W equals X transpose X inverse X transpose Y, where X transpose is obtained by interchanging the values of rows and columns of matrix X. So let us first calculate the term X transpose X. What we get is a 3 cross 3 matrix as shown here. And when we find the inverse of this term, we get the following matrix as shown here. Next, let us calculate the term X transpose Y. What we get is a 3 cross 1 matrix, and when we'll multiply this matrix with X transpose X inverse, we get the optimum value of weight W as a 3 cross 1 matrix as shown here. The first value in the column of W is the W0, next term is W1 and the last value is W2. This is the optimum value of W that we have obtained using multiple linear regression model. Therefore, when we will substitute this value into the equation, we get y equals 11.242 plus 0.479 x1 minus 0.152 x2. Now let us predict the value of y for capital X equals 2 and capital X2 equals 3. Here the value of y is equal to 12, that is our actual output is 12. So when we'll substitute x1 and x2 into the given equation of y, we get y equals 11.78 as shown here. So you can see that how close is our prediction. This is how we can predict the values of y using multiple linear regression formula of w. So you all might be wondering, okay human, we get it, but what about the derivation? How you come up with this formula? So don't worry, for all the nerds watching this video, let us start the derivation. There are two ways we can derive this formula. First is the calculus way, which involves a lot of mathematics, and other is through geometry, which is lot easier since here only simple visualization is involved. Just now we have seen that if we enter two inputs to our multiple linear regression model, we get the predicted output y as y equals w0 plus w1 x1 plus w2 x2. Now let us generalize this model. Let us say we have m inputs x1, x2 up to xm, and we get predicted output y as, this was for two inputs, now for m inputs it will become this. We can also rewrite this equation as this. I have just multiplied 1 with w0. Now in our example we had this dataset and we got the matrix S as follows. When you will observe carefully, you will find that the second column of x is equal to the values of column of x1. Similarly, the third column in x is equal to the values of columns of x2. The first row that you see in x, that is the column of ones, is the one that we have multiplied with w0. This ones that you can see is also known as bias in machine learning terminology. So we can rewrite this matrix x as x equals 1, x1, x2 up to xm, or we can also rewrite it as x equals x0, x1 up to xm. I have just replaced ones with x0. So this x0 is a column vector or just column of ones, and each and every element in x, that is x0, x1, x2 up to xm, are column vectors. So here we have m different inputs, and each input, that is x0, x1 up to xm, contains n samples or n datasets. Therefore we can rewrite our matrix x as follows. So the first column here is x0, second column is x1, and so on. And in each xij, where I denotes the ith input as shown by this red line, and j is the jth sample or jth dataset as shown by this red line. Therefore our x is n cross m plus 1 matrix, m plus 1 because m inputs and 1 bias. Now let us denote w as column vector with values as w0, w1, w2 up to wm. Therefore w will be m plus 1 cross 1 matrix. Also let us denote y as a column vector with values as y1, y2, y3 up to yn. Therefore y will be n cross 1 matrix. Now after getting familiar with the notations, let us jump into the derivation part. I have tried to simplify it as much as possible, so if you are stuck at any point, then do let me know in the comment section below. Let us consider a plane which represents the column space of x. In simple terms, column space of x represents a space in which if you multiply any column vector, say w here, with x, you get another column vector small y which lies in this plane or which lies in the column space of x as shown here. Now if there doesn't exist any column vector w such that xw equals capital Y, then this y lies outside of the plane or outside of the column space of x as shown here. So what is our objective? Our objective is to minimize the difference between the actual output and the predicted output, that is capital Y minus small y, and we are squaring it so that no negative term is involved here, as it might make our total error 0. Let us denote this difference by the red line as shown here, and let us call this difference as small e. So our error capital Y minus small y whole square is minimum only when. What do you think? Just pause the video and think about it. Yes, finding this minimum is equivalent to finding the minimum distance of capital Y from column space of X, and this shortest distance is the perpendicular distance, and it is possible only when this E is perpendicular to the column space of X. Now we have represented our X as this matrix as defined earlier. Also, the vector E can be defined as shown here. It will be the vector of capital Y minus small y. Then we can write our X transpose something like this. Therefore, when we will multiply this X transpose with vector E, we get this matrix. This matrix can also be rewritten as this. Here, the X and E inside these brackets represents the inner product of X and E. And here comes the main part. The inner product between any vector xj and E is equal to 0. Why? Simply because remember that our E vector was perpendicular to the column space of X, and the inner product of two perpendicular vectors is 0. Therefore, we get X transpose E equal to 0. Now we will use this to derive the well-known formula for the optimal value of W. For that, let us consider xw equals small y. We can also rewrite this equation as xw equals capital Y minus E. I have just substituted the value of small y as capital Y minus E. Now just pre-multiply the above equation with X transpose. Therefore, we will get X transpose xw equals X transpose capital Y minus X transpose E. And just now we have seen that the value of X transpose E is equal to 0. Therefore, we are left with X transpose xw equals X transpose Y. And now this X transpose X is a square matrix of dimension m plus 1 cross m plus 1, and if its determinant is non-zero, that is, it is non-singular, then we can find its inverse to get the value of W as X transpose X inverse X transpose Y. See how easily we have computed the value of W using geometry in an elegant manner. So that's it for this video. In the next video, we will be dealing with the most famous algorithm in the entire machine learning universe, which is gradient descent algorithm, and we will see how to predict the values of y using this algorithm. So if you like this video, then please give a thumbs up and subscribe and share this video so that I'll be inspired to make more such videos on ML. Also, if you have any queries, then do let me know in the comment section below. See you in the next video.